start with the puzzle plainly, because the whole investigation turns on it. Somewhere in the deep sky, in the direction of the constellation Boötes, sits a ring of galaxies so wide that light needs more than 1 billion years to cross from one edge to the other. It is real. It has been measured. And according to the rules cosmologists have leaned on for nearly a century, a shape that big is not supposed to exist. So what did the telescopes actually see, and how confident can we be in what they saw? That is where this investigation begins. The first thing worth understanding is how the ring was found in the first place, because the story matters. It did not arrive through a dramatic press event or a sweeping search designed to hunt for giant structures. It arrived quietly, buried in a survey of distant galaxy cores called quasars, the blazing centers of galaxies powered by supermassive black holes swallowing gas at extraordinary rates. Quasars are useful precisely because they are so bright. They act like faraway streetlights, letting astronomers trace the shape of matter sitting between us and them. Map enough quasars, and slowly, a picture of the deep universe starts to sharpen out of the noise. Somewhere inside that map, a shape appeared that should not have been there. Quasar after quasar lined up along a curve, closing into a ring nearly 1.25 billion light-years across, roughly 9.25 billion light-years from Earth, meaning the light we see now left that structure when the universe was still young, only a few billion years into its life. Picture that. A shape so wide that our entire Milky Way galaxy could be tucked inside a rounding error on its diameter. And it was already sitting there, fully formed, at a stage of cosmic history when structures of that scale were not supposed to have had time to assemble. The natural first reaction from any careful researcher is not excitement, it is doubt. Because the sky plays tricks. Patterns emerge in random data all the time if you stare long enough. A cluster of dots on a screen can look like a circle to the human eye without being a circle in reality. So the earliest and most important question was the simplest one. Is this ring an actual physical arrangement of galaxies bound together in space, or is it a shape our brains are imposing on scattered points that only happen to line up from our point of view? To answer that, researchers turned to redshift. When light travels across the expanding universe, its wavelength stretches. The farther a galaxy sits from us, the more its light gets pulled toward the red end of the spectrum on arrival. That stretch is measurable, and it works like a distance stamp. Two galaxies with similar redshifts are sitting at similar distances from Earth. Two galaxies with very different redshifts are separated by enormous stretches of space, even if they appear side by side in a flat photograph of the sky. Here is why that matters for the ring. If the shape were only a visual coincidence, a random scatter of unrelated galaxies that happen to look circular from our angle, the redshifts inside it would be all over the place. Some galaxies close, some far, no consistent depth. But when the measurements came back, they told a different story. The galaxies making up the ring sat at strikingly similar distances. They were not scattered across cosmic depth. They were clustered together in space, forming an actual physical structure rather than a flat illusion pasted across our view. That result did a lot of work. It moved the ring from the category of interesting-looking pattern into the category of measured object. Two different categories entirely. And the difference matters when the claim on the table is that a rule of cosmology may be in trouble. There was still another possibility to rule out, though, and this one is harder to dismiss casually. Massive objects bend light. A galaxy cluster sitting in the foreground can act like a lens, stretching and warping the light of everything behind it. Astronomers call this gravitational lensing, and it can produce shapes in the sky that look real but are not. A ring of light around a foreground cluster is a well-known lensing signature, common enough that any responsible team has to check for it before making a bigger claim. So the check was made. If lensing were the source of the shape, the galaxies inside the ring would show random, unrelated distances behind whatever lens was doing the bending. Lensing does not care about the true depth of the background sources. It just warps whatever light happens to pass through. The redshift data showed the opposite pattern. The galaxies clustered at consistent distances, exactly what you would expect from a real physical structure, and exactly what you would not expect from a mirage. The lensing explanation failed the test. That leaves one honest conclusion at the end of the first strand of evidence. The ring is a real arrangement of galaxies sitting together in space at a real distance from Earth. That much has been verified by independent checks from more than one research group. What formed it, why it took this shape, and whether it truly breaks the largest rule in cosmology, those questions are still open. But the object itself is no longer in doubt. We should sit with what that actually means, because it is easy to nod along and miss the weight of it. A structure more than 1 billion light-years wide, sitting in the early universe, arranged in a shape so clean it is hard to look at without feeling that something purposeful put it there. Nothing purposeful did, of course, but the mind reaches for that word because the pattern is so obvious. And obvious is the last thing a structure of this size is supposed to be. The rule most cosmologists were taught, and the rule that sits underneath most of the math they use every day, is that the universe should not build clean, obvious shapes at scales this large. Small clumps, yes. Local clusters, absolutely. But not a ring the size of a continent-sized cosmic neighborhood. Not one you can trace with a finger across a map. To weigh what the ring means, we have to step back from it, far enough back that the ring itself becomes a single feature inside a much larger picture, the shape of matter across the observable universe. That larger picture has a name, and it has only recently been mapped in the kind of detail this investigation actually needs. Space feels empty when you look up on a clear night. A few points of light, a lot of dark between them. That impression is misleading in a specific and important way. Zoom out past individual stars, past galaxies, past even the clusters of galaxies that gather in the hundreds and thousands, and a hidden architecture starts to appear. Galaxies do not sit scattered like sand thrown across a table. They gather along thin threads of matter, thread meeting thread at bright hubs where the density climbs highest, with vast, nearly empty regions sitting between the threads. Cosmologists call this arrangement the cosmic web, and the name fits the geometry almost too well. Filaments, nodes, voids, a structure that spans the observable universe and organizes almost everything in it. For most of the history of astronomy, this web was more of an inference than an image. Older telescopes could pick up bright galaxies clearly enough, but the fainter connective tissue between them, the dim outer edges of filaments, the sparse galaxies threading through voids, kept slipping below the noise floor. Researchers knew the web had to be there, because the mathematics of gravity acting on matter over cosmic time practically demanded it. But knowing a thing must be there and seeing it clearly are two very different achievements. For a long time, we were stuck on the first without quite reaching the second. That situation changed when the James Webb Space Telescope came online. Webb was built to catch light that other instruments could barely register. Light stretched into the infrared after traveling for enormous stretches of cosmic history, dimmed almost to nothing by the expansion of space itself. That kind of light carries information from the earliest epochs of galaxy formation, and until Webb, most of it was simply out of reach. With the new instrument feeding data into large collaborative surveys, the faint parts of the web finally came into focus. The Cosmos Web Survey, one of the largest programs Webb has undertaken, has been steadily building the deepest, sharpest map of this structure ever produced. Roughly 164,000 galaxies charted across a patch of sky about the width of 3 full moons laid side by side. Numbers like that are hard to feel. So try it a different way. Every dot on that map is not a star. Every dot is a galaxy. Each one holds hundreds of billions of stars of its own. 164,000 of them laid out across a slice of sky small enough that you could cover it with a fingernail held at arm's length. That is the resolution we are now working with. That is what detailed means in this context. What the map shows in broad strokes is more or less what cosmologists expected. Galaxies gather along filaments. Filaments meet at dense nodes. Voids stretch between them, sometimes for hundreds of millions of light years, mostly empty. The overall pattern, at least at first glance, looks like a scaled-up version of the pattern predicted by decades of computer simulations. The ones that model how ordinary matter and the invisible mass we call dark matter would arrange themselves under gravity over billions of years. That much is a quiet confirmation, and worth noting on its own. The general architecture of the cosmic web is not in doubt. The rules that describe how galaxies clump and thin out at ordinary scales, the tens and hundreds of millions of light-years, appear to be holding up against the new data, which makes the ring the obvious sore spot in the picture. Because here is what the map lets us do that no previous survey allowed. It lets us compare specific features in the sky against what the standard model of cosmology predicts should be there at each scale. Small clumps, predicted, present. Modest filaments, predicted, present. Large voids stretching a couple of 100 million light-years, predicted, present. A ring of galaxies more than 1 billion light-years wide, sitting in the early universe, closed into a clean circle, not predicted. Not part of the expected distribution, not something the standard formation timeline produces even when the simulations are run repeatedly under a wide range of starting conditions. The gap between the Webb, the models predict, and the ring sitting inside the sky is not a small mismatch. It is a categorical one. The models predict a certain amount of clumpiness at every scale, with the clumpiness smoothing out into near uniformity once you go big enough. The ring sits at a scale where smoothness is supposed to have taken over completely, and instead, we find a shape that would be hard to draw with a compass on a piece of paper. Some researchers have pushed back against the interpretation that this is a real problem for the cosmological picture. Their argument, in fair terms, runs something like this. Rare features do sometimes appear in random data, and the universe is very large. If you search enough patches of sky, eventually you will find something that looks improbable simply because you have given randomness enough chances to produce an outlier. This is a serious argument and it deserves to be taken seriously, but it also has weaknesses that the map is beginning to expose. The ring sits in a region that has already produced one other shape breaking the same rule: the earlier giant arc discovered in the same patch of sky. Two impossible-looking structures in the same neighborhood is a harder pattern to wave off as pure statistical fluke. And the deeper the surveys go, the more the coincidence hardens into something worth naming. Here is where the second strand of evidence starts to converge with the first. The ring, on its own, is a single anomaly. Real, verified, but singular. Placed inside the wider map of the cosmic web, though, it stops looking like a lone oddity and starts looking like a specific kind of failure of the standard picture. A failure at the largest scales, in exactly the places where the standard picture is supposed to be at its most reliable. That is a different kind of problem from a small local puzzle. It is a problem that reaches into the assumptions underneath the whole model. We should not overstate this. The map does not overturn cosmology. Most of the web looks the way the models say it should look. The general story of galaxies gathering along filaments over billions of years still holds. Dark matter still appears to be doing the heavy lifting in the background, shaping where matter collects and where it thins out. None of that has been erased by the new data. What has changed is that the map has given researchers a shared reference against which anomalies can now be measured precisely. Before, a strange structure in the sky could be brushed aside as a limitation of the instrument or a quirk of a particular survey. Now the instrument is Webb, the survey is deep and wide, and the anomaly does not go away when you look harder. It sharpens. Time is the piece of the puzzle we have not touched yet, and it is the piece that turns an already strange discovery into something genuinely difficult to place inside the current picture of the universe. Because a shape this size is one problem. A shape this size, sitting where we find it, at the moment we find it, is a different problem entirely. Distance in space is also distance in time. This is one of those facts that sounds like a poetic flourish, but is actually a hard rule of physics. Light travels at a fixed speed, and the universe is enormous. So every image we collect from a distant object is an image of that object's past. The farther away it is, the older the picture. When telescopes catch light from a galaxy sitting billions of light years away, they are not seeing that galaxy as it exists now. They are seeing it as it existed when the light left it, long before Earth was a rocky ball, long before the sun had formed, long before most of the elements in our bodies had been forged inside the cores of dying stars. The ring's light has been traveling for something like 9 billion years to reach us, which means we are not looking at a mature, settled feature of the modern universe. We are looking at a snapshot of a much younger cosmos, a cosmos that was only a few billion years old when whatever we are seeing had already assembled itself into the shape we now measure. That timing is the entire heart of the problem, and it is worth slowing down to feel the weight of it. Structures in the universe, according to every mainstream model researchers use, are supposed to grow the way a snowball grows on a hillside. Slowly, patiently. A small clump of matter pulls in more matter through gravity, becomes a larger clump, pulls in still more. Larger clumps merge with other larger clumps over unimaginably long stretches of time, eventually building the galaxies, clusters, and superclusters we see around us. That timeline is not a rough estimate. It is a carefully calculated process built on decades of observation, simulation, and refinement. The mathematics behind it is dense, but the shape of the story is simple. Small first, big much later, very big much later than that. The ring does not fit that shape. At the point in cosmic history where we find it, gravity has not had enough time to pull together something on this scale. It is like walking into a garden that was planted last spring and finding a fully grown, deep-rooted oak tree already casting a wide shadow across the lawn. The materials could be there in principle. The years to grow them into what you are looking at are not. Try a different comparison, because the scale of the mismatch is worth landing precisely. Picture a project handed out in a classroom on a Monday and due back on Friday. Now imagine that the project actually requires half a year of concentrated work to complete honestly. On Friday morning, a student walks in with the finished project sitting neatly on their desk, every detail in place, no visible shortcuts, no evidence of anyone else having helped. That is roughly the situation cosmologists are facing when they try to reconcile the ring's size with its distance in time. The universe seems to have finished an assignment far earlier than the timeline says it should have been able to finish it. Here is where the interpretive work gets genuinely difficult, and where honest uncertainty matters most. One camp of researchers argues that the resolution to this timing problem is going to be found inside the existing framework. Their case is that we may simply be missing an ingredient in our current models. Some detail about how matter behaved in the early universe that once identified would let structures grow faster than current calculations predict under specific rare conditions. This is a reasonable position. Science is full of examples where an anomaly that looked catastrophic turned out to be a call for a subtle refinement rather than a full replacement. The rule was fine. The application of it needed sharpening. Researchers holding this view are not dismissing the ring. They are betting that the fix, when it comes, will fit inside the existing structure of cosmology without breaking it. Another camp is willing to consider something more unsettling. Their position is that the timing problem may be pointing to a formation process that is not yet part of any mainstream model at all. Not a tweak to the growth rate, not a missing ingredient. An entirely different mechanism by which matter can organize itself into large structures under conditions that existed only in the young universe. What that mechanism would be, no one can currently say. That is the honest state of the argument. Researchers in this camp are not claiming to know the answer. They are claiming that the anomaly is severe enough to justify looking for an answer outside the boundaries of what has already been tried. Both positions are being held by careful people. Neither has been ruled out. The evidence, as it stands right now, does not force a choice between them. What the evidence does force is a specific kind of intellectual honesty. It says that the standard timeline for cosmic structure formation, as currently written, does not produce a ring of this size at this distance in time. That is not a matter of interpretation. It is a matter of running the numbers. The models have been run, and rerun, and adjusted, and rerun again, and the ring does not fall out of them naturally, which means one of two things has to be true. Either the numbers going into the models need adjusting, or the process being modeled is not the whole story. The idea that a completely unknown formation process might be at work sounds dramatic when written down in a single sentence. In practice, it is a much quieter possibility than it sounds. Cosmology has room for unknowns. It always has. Dark matter, whatever it turns out to be, is a placeholder in the current models for a form of matter no one has yet identified in a laboratory. Dark energy, the term for whatever is accelerating the expansion of the universe, is even less understood. The field is already carrying two very large question marks at the center of its accounting. Adding a third, an unknown process capable of assembling large structures faster than gravity alone would allow, is not the sort of proposal that would send cosmologists running for the exit. It is the sort of proposal that would be examined carefully, tested against as many independent observations as possible, and either accepted or set aside on the strength of the evidence. There is no verdict yet. That is worth saying plainly. Researchers disagree on this, and the disagreement is not going to be resolved by the ring alone. It will be resolved, if it gets resolved, by more data, more surveys, more anomalies pinned down or explained away, more careful checks of whether the timing problem the ring raises shows up in other regions of the deep sky as well, or whether it stays confined to this one strange patch near Boötes. If it stays local, the balance of evidence will probably tip toward the "we are missing an ingredient" camp. Local anomalies usually point to local causes. A rare configuration of matter, a chance alignment, a piece of the map where several small effects added up in an unusually visible way. If, on the other hand, the timing problem shows up again and again in other deep surveys, in other patches of sky, at similar distances, that would be a much harder result to explain by refining the existing framework. The evidence would start to look less like a single anomaly and more like a signal, a hint that the process by which the young universe built its largest structures ran on rules that were not fully captured in the models we currently use. We are not there yet. What we have right now is one ring, one arc in the same neighborhood, one deep map that lets us see how well the standard picture holds at every other scale we can check, and one specific place where the picture does not hold. That is not enough to overturn cosmology. It is enough to force the question, which is exactly what a healthy science does with anomalies. It does not ignore them. It does not rush to declare them the end of the old story. It sits with them, tests them from every angle it can find, and lets them push the field toward better questions than the ones that were being asked before. The ring is a better question than cosmology had a few years ago. Whatever the answer turns out to be, a refinement, a replacement, or something no one has thought of yet, the shape of the field will not look quite the same on the other side of it. The evidence suggests that much, even if it cannot yet suggest what specifically is coming next.